Week 5 to 6, Evaluating Classifiers, Accuracy, Precision, Recall, and F1-Score. Welcome to this lesson where we explore how to evaluate machine learning classifiers. We will talk about concepts, write code, and do hands-on exercises. These metrics help us understand how well our models perform in real life. We will use the Telecom customer churn dataset and the Titanic dataset. Let us start with a quick overview of why evaluation matters. Running the cell now. Why do we evaluate classifiers? Building a model is only half the job. Evaluation tells us if predictions are meaningful or misleading. Wrong metrics can hide problems. Today we will avoid common pitfalls. Running the cell now. First, let us prevent warning messages from cluttering our work. We are turning off warnings, so our outputs look clean and simple. Import NumPy as NP. We set the random seed to 42 for reproducibility. Running the cell now. This code sets a random seed and suppresses warnings to ensure consistent results and a clean output during model evaluation. While there's no visible output here, this setup is crucial for reproducibility and a distraction-free learning environment when we later assess classifier performance. It supports our lesson goal of focusing clearly on meaningful evaluation metrics. Try typing this out and see how your notebook feels cleaner. Let us load the Telecom customer churn dataset. This data is often used to predict if a customer will leave a service. We import pandas. We load the Telecom customer churn dataset from a public IBM GitHub repository. We print its shape and preview the first rows. Running the cell now. This output gives a quick overview of our Telecom dataset, with 7,043 customers and 21 features capturing demographics, services, and payment details. Notice the mix of numeric and categorical columns like tenure and contract, which are crucial inputs for predicting churn. Understanding these data shapes and types sets the stage for building and properly evaluating classifiers later in the lesson. See if you recognize any columns. Can you guess what a churner means here? Before we start modeling, let us make sure our data does not have missing pieces. We check for missing values in the data set. Running the cell now. Here, we check for missing values in the dataset and see that none of the key columns have any null entries. This confirms our data is complete, ensuring that evaluation metrics won't be skewed by missing information. Proper data quality is essential before assessing how well our classifier performs. Try using .isnl, .sum on other datasets you use. Data cleaning time. We remove ID columns that do not help prediction. We also drop rows that have missing data for now. We drop the customer ID column. We remove rows with missing data. Now our data has only useful records. Running the cell now. Here, the output, 704320, shows the shape of the clean dataset after dropping the customer ID column and rows with missing values. Notice how the number of rows confirms how much data remains for model training and evaluation, which is crucial because incomplete or irrelevant data could mislead our classifier's performance metrics. This step ensures we evaluate the model on a reliable, consistent dataset, aligning with the lesson's focus on meaningful evaluation. Can you think of reasons why IDs do not help the model learn? Machine learning models need numeric data. Let us convert text columns into numbers. We look at each text column. We turn categories into codes so the computer can use them. Now we see numbers instead of words. Running the cell now. Here we see the first 3 rows of the dataset after converting all categorical text columns into numeric codes. Notice each original category is now represented as an integer, which is essential for many machine learning models that require numerical input. This step ensures our classifier can properly interpret the features before we evaluate its performance. Check out which columns were converted. It is a useful habit in every project. Now, let us separate our target column, which shows if a customer churned, from the features. We create X to hold our features. We create Y to hold the churn label. Running the cell now. Here, we separate our dataset into features, X, and labels, Y, isolating churn as the target variable. This step is crucial because it frames what the model will learn from features versus what it will predict, labels. Without this clear split, evaluation wouldn't be possible since we need true labels to compare against predictions. Try this split in your own datasets as practice. To know how well our model will perform on new data, let us split our dataset. We bring in a function to split our data. We use 75% of data for training and 25% for testing. Using a random seed makes results reproducible. We show the size of each split. Running the cell now. This output shows the shapes of the training and testing feature sets after the split, with 5,282 samples in training and 1,761 in testing, each having 19 features. Noticing these counts confirms that 25% of the data is reserved for testing, which is essential for unbiased evaluation of the classifier's performance later. This step ensures our model's predictions are assessed on unseen data, aligning with the lesson's emphasis on meaningful model evaluation. How does this split help us avoid overfitting? Let us try a classic method. Logistic regression is a simple yet strong classifier. We import logistic regression, a basic classification model. We create the model and set the max iterations. We fit the model to our training data. Running the cell now. The output confirms that the logistic regression model was successfully created with a maximum of 500 iterations for convergence. This step is crucial because it sets up the classifier we will later evaluate to ensure its predictions are reliable. Remember, building the model is just the start. Evaluation tells us if this trained model truly captures meaningful patterns. Have you used logistic regression before? Can you think of its use in real life? Now, we see what our model predicts on new data it has not seen yet. We use the model to predict churn for the test set. Running the cell now. Here, the code uses the trained model to make predictions on unseen test data, producing the array y_pred. Although there's no printed output, this step is crucial. It generates the predictions we will evaluate next to understand if our model truly performs well or if it's leading us astray. This sets the stage for selecting appropriate metrics to assess prediction quality meaningfully. Did you expect the predictions to be perfect? Why or why not? Understanding accuracy. Accuracy is the fraction of correct predictions out of all predictions. Works well when classes are balanced. Can be misleading for imbalanced data. Let us compute it next. Running the cell now. We use a handy function to measure what fraction of our predictions are correct. We import a function to compute accuracy. We calculate and store the accuracy of our model. We print the result so we can see how well the model does. Running the cell now. Here, the accuracy of approximately 81% indicates that the model correctly predicted labels for 81% of the test samples. While this seems promising, in this lesson's context, it's important to remember that accuracy alone can be misleading if the classes in the data are imbalanced, as it doesn't reflect the distribution of errors across different classes. Now try to explain accuracy in your own words. Precision and recall. Precision answers, of all predicted positives, how many were truly positive? Recall answers, of all actual positives, how many did the model find? Both matter if making mistakes is expensive. Running the cell now. Let us see how many positive churns the model really caught, and how many it found correctly. Precision is about being correct when predicting churn. Recall is about finding all the real churners. We import functions to compute precision and recall. We calculate precision for positive predictions. We calculate recall to see coverage of actual positives. We print both numbers so we can compare. Running the cell now. This output shows the precision of about 0.70 and recall around 0.55, meaning the model correctly identified 70% of the predicted positives, but only found 55% of all actual positives. Notice that while precision is relatively high, recall is lower, indicating the model is more conservative in labeling positives and may miss true cases. This highlights the trade-off between precision and recall we must consider when mistakes have different costs. Which do you think matters more for churn, precision or recall? What is F1-Score? F1-Score combines precision and recall into one metric. It is their harmonic mean. Best when you want a balance between both. Running the cell now. Time to unite precision and recall into a single score. We import the F1-Score function. We compute the F1-Score for our model. We print out the value. This gives us a single summary score. Running the cell now. The output shows an F1-Score of approximately 0.62, reflecting the balance between precision and recall for the model's predictions on the test data. This metric indicates that the model has a moderate balance of correctly identifying positive cases without too many false positives or false negatives. In this lesson, notice how the F1-Score consolidates these two aspects into a single value, helping us evaluate overall classification performance when both precision and recall matter. Can you spot cases when F1 matters more than accuracy? A confusion matrix shows us true positives, true negatives, and our mistakes. We import a tool to build the confusion matrix. We get the matrix for our predictions versus the truth. We print it to understand where the model made mistakes. Running the cell now. This confusion matrix shows the counts of correct and incorrect predictions by class, with 1166 true negatives and 265 true positives indicating fairly good classification. The off-diagonal values, 116 false positives and 214 false negatives, highlight the types of errors affecting precision and recall. Understanding this balance is essential because the F1-Score combines these two metrics to give a single performance measure, especially when you want to weigh false positives and false negatives equally. Try to label each box. What is a true positive here? Instead of checking one metric at a time, let us see a summary report. We import a function for a full metrics report. We print precision, recall, F1, and support for each class. Running the cell now. This classification report summarizes the model's precision, recall, and F1-Score for both classes, showing how well it balances false positives and false negatives. Notice that Class 0 has higher precision and recall, leading to a strong F1-Score of 0.88, while Class 1 has lower recall and F1-Score, indicating the model struggles more with that class. This output demonstrates why the F1-Score is useful. It captures this trade-off between precision and recall in one key metric. Practice. What does supports mean in this report? Look it up and explain. Switching datasets, Titanic. Let us try a totally different dataset to check what happens when class sizes change. Ready? Here we go. Running the cell now. Now we load the Titanic dataset. This is a classic for survival prediction. We import pandas. We load the Titanic dataset from a public GitHub repository. We print its shape and preview the first rows. Running the cell now. The output shows the Titanic dataset has 891 rows and 12 columns, indicating a moderately sized dataset with multiple passenger details. Notice the key columns like survived and P-class, which will help us observe how class sizes and survival rates differ in this new context. This printout confirms successful data loading and sets the stage for analyzing changes compared to previous datasets. What columns might you use as features to predict survival? Let us pick simple columns, drop rows with missing data, and encode as sex res numbers. We select survival, class, sex, age, number of siblings or spouses, and fair. We drop any rows that have missing values. We turn that sex column into a number so models can use it. We make X2 as our features, and Y2 as the target. Running the cell now. Here, we've selected key Titanic features and cleaned the data by removing missing values to ensure consistent input. Notice how we've converted that sex column into numerical codes, which is essential for machine learning algorithms to process categorical data. This step sets the foundation for modeling by preparing a cleaner and more structured dataset tailored to the Titanic survival prediction task. Try selecting your own set of features using a different dataset. Let us split the Titanic dataset too, so we can train and test fairly. We split Titanic example data into training and test sets. We use the same random seed for reproducibility. Running the cell now. Here, we split the Titanic dataset into training and testing sets, reserving 20% of the data for testing. Notice that there is no direct output because the focus is on preparing the data for modeling, ensuring that both sets represent the class distributions accurately for reliable evaluation. This step is crucial when working with a new dataset to handle varying class sizes properly. Why is split size sometimes different? Here, 20% test. Let us see how the Titanic classifier does. We will run a report just like before. We import and create a logistic regression model. We fit the model to the Titanic training set. We make predictions on new, unseen data. We import a summary reporting tool. We print accuracy, precision, recall, and F1 for all classes. Running the cell now. Here, the classification report shows how our logistic regression model performs on the Titanic dataset, with class 0, not survived, having higher precision and recall than class 1, survived. Notice the support columns indicate class imbalance, which helps explain the difference in scores. This output highlights how changing datasets and class distributions can impact model evaluation metrics. How different are the scores compared to the Churn dataset? Compare them and discuss. Practice and try it yourself. Switch back to your favorite dataset. Compute accuracy, precision, recall, and F1 score. Notice how the numbers change as you modify the data. Running the cell now. Want to master model evaluation? Type the code and leave a comment with your favorite metric below. Need extra challenge? Try building a function that reports all the evaluation metrics for any classification model and dataset. Bonus, visualize the confusion matrix as a heat map. Running the cell now. Recap. Today you learned about accuracy, precision, recall, F1 score, and the confusion matrix. You also practiced with 2 real-world datasets. These skills help you know when your model is really working. Keep practicing. Running the cell now. Thank you for learning with us. Like, subscribe, and share if you want more beginner-friendly Python and data mining tutorials. Try out what you learned. See you in the next video. Running the cell now. Can you think of a real-world scenario where F1 score would help you decide between models? Share your answer and subscribe for more hands-on lessons.